Okay, hello everyone. Welcome to our second part of the Transformers lecture. A couple of announcements today. The fourth assignment is due tonight, so please make sure to submit it by 11:59. And our second midterm has been pushed back to November the 25th, which is not this Monday, the other one, I think. But yeah, last time we were talking about transformers. We motivated them from the RNN's perspective. We saw that RNNs have have a bottleneck when you are doing machine translation because you have to pass the hidden state from the encoder to the decoder. And because they are inherently recurrent, we need a for loop, which is hard to parallelize, and then that affects the amount of data we can actually, or the speed of training of these models, and then transformers, they come as a solution to these, because now we have a model that is fully based on attention. It doesn't have a recurrency anymore, so that for loop has been removed by design, right? And we saw that the attention mechanism that the transformers use is slightly different. It's called scale.product attention because it uses the dot product to compute similarity between words and then scales these similarity down based on the dimensionality of the learned matrix. And also, there's a couple of ideas that have been introduced here, for instance, self-attention, because now the transformers, they can compute attention based on the input sequence itself, right? Back in RNNs, we were computing attention based on an entire given sequence to decode another sequence. And now the actual input sequence, or the source sequence, is used to compute self-attention. So it's the attention of a word to its neighbors in the input sequence, and all its neighbors. And because of that, there is a property of transformers that I didn't mention, which is actually very important. Because the way they compute self-attention, the transformers have a certain limitation because they can only process sequences of a given length, which is different than RNNs. RNNs are more flexible because you can potentially model an infinite sequence. Right? If instead of that for loop you have a while, let's say a while true, you could potentially at every time step update your hidden model, and you can do that forever. Right? But here you cannot do that because the self-attention is limited to a certain window size, which when you're programming, normally you call that sec-len or sequence length. These are normally the arguments or the names used for variables. But so you have to pick a window size to process the sequences. So this is actually a limitation. And it makes sense, right? Because it's like the transformers are unrolling the RNN over time for a fixed amount of time steps. And then, okay, that's self-attention. Then we saw that you can actually learn multiple attention matrices, similarly to what we do in convolutional neural networks. Like there we learn multiple filters. Here we learn multiple weight matrices. That's why we call it multi-head attention. And then we concatenate all these learned representations to form a kind of a very complex representation for each word of the sequence. But then we use positional embedding or encoding, to add positional information to this learned representation, because the original attention representation doesn't care about position. So the words could be in a different permutation, and the attention matrix would not care much about that. But the positional embedding or the positional encoding helps adding this position information to the words themselves before you compute attention. So the attention mechanism has to look at the positions while trying to attend to different words. Okay? And then we saw that for training, we need to do a masked multi-head layer because we want to train these things in parallel. But the model, when you're doing inference, it has a for loop in it because you are doing autoregressive decoding. So you start with a token, get sample the second one, concatenate back, and sample it again. So that procedure is actually a loop. But we don't want to do that in training, right? So avoid that procedure during training. We do masked multi-head layer, which simply just like zero the corner of the upper corner of the attention matrix. So we cannot look at the future words, right? So a given words can only look back. It can never look to the future. And that on its own is sufficient for training this model in parallel without having that for loop. Any questions before we start, or comments or anything? So for today, we're gonna see two very important transformer-based architectures. Perhaps you all know most of the things we're gonna talk about today. Hopefully I can add some new things. But we're going to talk about the GPT model, which stands for General Pre-training, and the BERT model, which stands for Bidirectional Encoder Representations from Transformers. Okay? So you probably have heard these words before, or these models before. But the motivation here is contextual word embeddings. We saw in that word embedding lecture that the embeddings we learn with Word2Vec and GloVe, they are static. And Transformer, they can learn kind of contextual, dynamic word embeddings. But regarding GPT, we're going to see this idea of fine-tuning or pre-training fine-tuning, that GPT was actually the model who introduced that idea in the context of natural language processing. And then we can see how GPT can generate text, which is the same principle as we saw in RNNs. Because GPT is a language model under the hood, so it can generate text in the same way that we've done with RNNs. It's just now based on the transformer model. But the formulation or the model is the same, probability of the next word given the previous words. And then we're going to talk a little bit about ChatGPT, which is kind of the most popular, maybe deep learning model these days. And see how ChatGPT is built on top of GPT. Then we're going to move to BERT and see this idea of masked language model, because BERT is not a regular language model, so it doesn't predict the next word. It does a different modeling. And we're going to see how to do word and sentence embedding using BERT. In principle, you can use GPT to also extract word or sentence embeddings, but BERT is typically more popular to do that. Okay. All right. So to start, I like to remember this idea of word embeddings, right? When we talked about Word2Vec and GloVe, we talked about this idea of learning an embedding matrix, which has in each column an embedding or a vector for any word in our vocabulary. So we use this example of man, woman, king, queen, apple, and orange. And we saw that we have this featurized representation where each row is a feature. And we can learn as many features as we want. We just don't know what they represent. Okay? And the basic way you use an embedding matrix is just multiply. You multiply by that matrix E by the one-hot encoding of the vector to get the embedded version or the embedded representation of that word, which in this case I'm showing as an example how you would get the orange embedding. You would just multiply the one-hot vector of orange by E, E is on the left, right? And then you get that last column of the matrix. But there's a problem, because this is a static matrix. Once you learn it, you would give the same dense vector for a given word, regardless of where the word is in a given sentence. So we talked briefly about this. Right? If you had these two sentences, I want a glass of apple juice and I work at Apple, to extract the embedding of the word apple, in these two sentences, you would multiply this, the one hot encoding of apple by that E matrix, it would give you the same result. Right. But clearly the words, even though they are the same, they have completely different meanings. Right? In the first sentence, apple is related to a fruit, or has as a meaning a fruit, and in the second, it's a company. So it's a completely different meaning, even though it's the same word. Okay? And it's a different meaning because they are in a different context, right? We know that the meaning apple is different because of the other words, right? So that's what a transformer can do to us. It can actually learn a different representation for a given word based on the surrounding words, so based on the context. So here's the figure of the encoder-decoder of the transformer, or the entire architecture. And here's a visualization of a few words I generated, or sentences, I generated, in two different styles. So the blue ones, or the blue dots, they are sentences where Apple is a company. And the orange crosses, they are sentences where Apple is a fruit. So you have here, for example, the apple tree is in our garden. There is a fresh apple in my, I ate a red apple for breakfast. So you see that in all the sentences where apple is a fruit, so this embedding, which I'm calling the contextual embedding, and was extracted by BERT in this case, so this is a real example. So if you use BERT or a transformer to get embeddings for a word, you see that the model or the transformer will be able to group these words, or to produce different embeddings based on the context. So each dot here is actually the embedding of the word apple, okay? Not in a different context. It's not the embedding of the whole sentence. I'm just showing the sentence there so you know what was the context, but this actually proves that for the same word you have different embeddings. And this is where I think this is one of the most, or one of the key points that make transformers really stand out. Okay. Because before transformers, I don't know any other model that could do this. Okay. So basically, to extract contextual embeddings from transformers, we're not going to do that using a machine translation framework. We're going to do that training a language model, as we did with Word2Vec. Actually, even before that, I showed you that very first example that used a language model to get an embedding. And there is basically two ways you could build a language model. You could use the encoder or the decoder. You don't need both of these networks, because in language modeling, you have a sentence, you're predicting the next word. So there's no source sentence. There's nothing I want to transform on anything. I just want to predict the next word. So I don't need these two networks. So I can use either one or the other. So that's what we have in terms of transformer language models today. Basically, all the GPT-based models, they use the decoder of the transformer to train a language model. And the BERT models, they use the encoder. But all of them are language models. We will see that the BERT language model is slightly different. It's called masked language model. And perhaps because of that, it actually extracts better embeddings than GPT. So GPT, or General Pre-trained, is this model designed by OpenAI back in 2018. I'm going to add the references, okay, at the bottom later, so you can look at the papers. So I think this is back to 2018. This is 1 year later, the original transformer, which was in 2017. And OpenAI was interested in using transformers for language modeling, okay? Because that wasn't done before. But since machine translation is a kind of conditional language modeling, because the decoder of the sec-to-sec model is by definition a language model, but it's a language model that is conditioned on a source sentence. So you could, in principle, just remove the encoder and learn a language model with the decoder, and that's what they did. So they trained a language model in a bunch of unlabeled text. And remember, this is basically trying to predict the next word given the previous word. So here I have this example, start of sentence, I want a glass of apple, and then the model tries to predict juice. So see here, there's a couple of differences. Since first of all, I don't have the encoder. This is just a decoder. But second is I don't have that multi-head layer in the middle of the model anymore. I just have the bottom masked multi-head. If you remember from the previous slides, we had here in between, exactly here in between these two blocks, we had another multi-head layer which had the Q and V, the K and V coming from the encoder, and the Q was coming from the decoder. But now, since I don't have an encoder, I don't need that layer anymore. So the model is slightly simpler. It's a slightly simpler decoder. Okay. So once you train your model for language modeling, you can just remove that language model head, we call it, or that softmax and fully connected layers that were on top. You can just throw them away. And freeze the weights of this language model. Okay. By freezing, I mean you just take the matrices and you load them, but now you're not going to change these weights anymore. Okay. And we can use this trained language model to extract contextual embeddings. Okay. So then what is cool about this is I can just simply switch or substitute the language model head by a classification head. So I add a new fully connected layer. Now it's a sigmoid because I'm using here as an example a binary classification problem, sentiment analysis. It's either negative or positive, so it's either 1 or 0. But those two layers on top, they are new. They are fresh weights, randomly initialized. But these weights here, they were trained before on language modeling task. That has nothing to do in principle with sentiment analysis. It's just predicting the next word. But it turns out that when you do that, or you do the first step, the embeddings you extract here at the top of the decoder, they have really nice properties. Like they are real good embeddings and semantic embeddings. So they help in many other tasks, like sentiment analysis or named entity recognition and other NLP tasks. So this is awesome because we just got extra performance in many different classification tasks by leveraging unlabeled data. So this was revolutionary actually, because like unlabeled text we have a lot like online, but like labeled data is much harder to get. So it's amazing that you can improve your supervised learning models using unlabeled data. Okay. So this really became revolutionary, and this is actually one of the standard approaches for any NLP task these days. If you're working with natural language, most likely you're going to use something like this. You're going to use a pre-trained model that came from somewhere or was trained by Google or some other big tech company because they trained this very large model that you don't have to retrain anymore. You can just use it to extract embeddings. You don't change the weights of this model. Okay. Obviously, you could if you wanted, and that's actually, you can do that. But the easiest way or the cheapest way you can use these pre-trained models is by just using them as a word-to-vec. It's just a large word-to-vec that gives it to you contextual embeddings. Okay. What is cool here? What is cool here is that now, let's say we had a data set of this, right? Of label data now, of labeled sentences or reviews. These are movie reviews. Okay. There is a famous data set called IMDb data set that actually came from IMDb reviews. There is a list of movie reviews like this. You would have like, this movie is great, like, I loved this movie, right? And this would be positive or 1. And then you would have maybe, I hated this movie. Or this film. Let's just use a different word, film. This was negative, okay? Let's say, well, because to build this data set, you need someone to come here and put a label in each of these examples. In practice, these data sets are typically much smaller. Even though they might have, I don't know, maybe 20K examples, maybe 100K, but they're still much smaller than, let's say, the data that ChatGPT was trained on, which is the entire internet. Right? So it's still, we call, in deep learning these days, this is still a relatively small data set. Okay? Because the sizes are just increasing very quickly in terms of unlabeled data. And obviously in IMDb, since it's a forum, there's many people tagging things, right? So you can build this data set much faster. But anyways, let's say this is a 20K example data set. Okay, so we have 20K lines here. You could train a sentiment analysis classifier, okay? So you can build a classifier, just call it classifier. It's a binary classifier. Maybe it's like just a logistic regression. X, sigma, just very simple logistic regression. Right. To predict either 1 or 0, positive or negative. So let's say if you train these two weights here from scratch, looking only at this data set, maybe your axes here are one-hot encodings. Or even in, like, they might be embeddings from word-to-vec. Let's say you could, by training this model, you could have maybe 72% accuracy. Okay? But by leveraging a transformer, right, you would take the same 20K words or data set, pass this through a transformer, and this could be a GPT or a BERT. Okay? And this is a frozen model, so you don't retrain it. You just pass it through GPT or BERT. And then you have the same classifier on top. Which is a logistic regression, WX plus B. And you have the same task here. You should just simply do that to extract embeddings now. You could bump up this to maybe 96% or something. And this was solely only trained on unlabeled data. So this model doesn't know anything about sentiment. It just knows how to predict a word, but still can help you with sentiment analysis and any other classification tasks. Okay, that's what we are doing here. And this step 1, training this model normally is called pre-training, and training then this model on top of this is called fine-tuning. Okay. So there is a detail. Now I'm going to go back to GPT only, just because we are focusing on this model for now. Oh, let me just write here that we are basically extracting embeddings. Here, you could call it, yeah, E or something because of embedding. But there is a detail when training GPT and other transformer models, which appears a lot and is actually important. So it's not part of the transformer. It's actually a separated algorithm, completely separated, but it has been used frequently when training these transformers, which is the byte pair encoding algorithm. Basically what it does, it takes the raw vocabulary, which is extremely large, as we already have seen. So our vocabularies in any language tend to be extremely large, right? Our vocabulary. So let's say you could have A, right? Then all the words with B, and then blah, 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 and then all the words with Z. So this could be up to, I don't know, 500K words, right? So this is still a problem, right? So the idea of byte pair encoding, or BPE, should just reduce this or optimize this vocabulary. So I want to reduce it as much as I can. So maybe bring it down to maybe from 500, maybe 100K. That would be great, right? If you could just have a smaller vocabulary. So that's the idea, or the motivation. And it does that by combining sequences of characters that are very common in a given vocabulary. Okay? So, for example, the suffix ing appears extremely a lot, and it will appear in many of the words here. Right? Playing, right? Carrying, right? Teaching, all the words, they will have to be here. So why not just combine this as making this one token? Maybe call it I or something. Somehow you make it a token, and then you just have the word play and maybe teach, and somehow you can combine these two things instead of having a copy of each one of them. But the overall idea of byte pair encoding is building a new vocabulary, like by combining common word pieces, and you do that by repeatedly combine the most frequent pairs of characters. So you first get all the unique characters in the vocabulary, and then for each sentence, you're going to count the amount of pairs of characters that are very frequent. Okay? And let me show you an idea. So it is a very simple example. You could have this extremely basic corpus of text, like low, lower, and lowest. And here it's interesting because obviously these three words have the same prefix, low, right? So initially, the algorithm is going to split all these characters, and then you would have this, let's say, you would represent your initial text as this, all these separated characters, okay? And then the algorithm works in a loop. So it first combines, it looks at the most frequent pair of characters, which in this case is low, L-L-O, right? So then it's going to combine now these two, low, this, and this. So see that the result is now low space W, low space W-E-R, low space W-E-S-T. And now it's going to look at the most frequent combination of, now it's, you have to look at the word level as well, right? Because low became a token or a word. So now L-O-W, you're going to combine these two because they are the most frequent pairs of character of tokens, let's say. And you keep doing that, right? So you just look at neighbor characters or tokens and you keep combining them until you have your vocabulary with a given size. So you have to, this algorithm assumes you're going to give a desired vocabulary size. Let's say 15 or 100. I want to control this number here. Okay. And then this is a while loop that runs until you get to this size. Okay. And I have a collab here. I'm going to link this later. But yeah, here is a simple BP tokenizer class. So you have to pass a vocabulary size that you want. Okay, and this structure here is going to store the final vocabulary. And here are the merge rules, those rules that we saw on the slide. Okay. So here, this function just counts that frequency of adjacent pairs of tokens. Right? You have to do this at every step. Here is just a function to merge the vocabulary. And here is the function that learns the BPE encoding. Right? As you'll see, this is a deterministic algorithm. Okay? There's nothing random here. So you start by initializing your vocabulary with all the characters. So you just have, so your initial state is your vocabulary has all the characters. And then this is the loop I was showing there. Okay? You find the most frequent pair, and then you add the merge tokens to vocabulary. You start here just storing the rules, right? And then you apply the merge rule. So I'll let you play with this if you're interested, but here there is a running example, right? Here the data set is formed by low, lower, lowest flow, flower, and flowing. And here's the result. So the initial this is the final vocabulary. Okay. E-F-G-I-L, low, lowy, lower, N-O-O-R-S-T-W. Okay. For this configuration, right? Here we set the vocabulary size to 15. So there should be 15 tokens here. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. So this is the output of the algorithm. And here are the merge rules. Okay. And here's an example. If you're tokenizing lower flower, you would get these tokens. And now this is a token, right? So this is interesting. Now E is a word for us. F is a word. G is a word. I is a word. Okay. I mean, it's an entry in the vocabulary. Okay. So this algorithm is kind of really cool because it can mix characters and prefixes and suffixes to optimize your vocabulary. Anyways, I'm showing this because this is very common pre-processing step, okay, when training these language models. Okay. But anyways, I wanted to point this out because this will appear actually in tutorials. This will appear when you're trying to reproduce transformers, like, oh, there's a BPE encoding, right? And I wanted to note that this is just a simple algorithm to compress a vocabulary. So here is a summary of the GPT models so far. It's an evolution over time. I think this is fun to look at because we can see how things are moving fast. So here in the first column we have GPT-1, was released in 2018. That model had 117 million parameters, and that was 12 decoder blocks stacked on top of each other. And they use roughly about 5 gigabytes of text for training that model. And at the bottom here, sorry, this is not pre-trained data set. This should be kind of main contribution. So GPT really introduced this idea of generative pre-training on NLP. This was the major kind of contribution. And back then, it already showed some improvements over the state of the art of many classification tasks in natural language processing, like sentiment analysis or named entity recognition. Okay? I'm going to again link the papers at the bottom over the slides so you can click on them and look at the results. It's actually very informative and interesting. And then came GPT-2 in 2019 with an extremely big push, right? From 117 million, now GPT-2 has 1.5 billion parameters, right? It's much bigger, right? And from 12 decoder blocks, GPT-2 has 48, 4 times, right? And it was trained obviously on much larger data set, now 40 gigabytes, because the model is bigger. And here, this model really started to surprise people in terms of text generation. Because I remember those two models, but I remember in 2019, GPT-2 was really the moment we thought, well, this is actually getting surprisingly good. Because it was generating this coherent long form text, right? And exhibited this surprising zero-shot learning abilities. When you say zero-shot learning abilities, is this capability of solving a classification problem without looking at one single example. So GPT-2, right? So here is a classifier or a sentiment analysis classifier that was trained on 20K samples of pairs text sentiment. GPT could solve that problem even without fine-tuning, with a very good accuracy. So you could just literally ask it, what is the sentiment, or what is the sentiment of this sentence? And it will give you its positive or negative, without even looking at one single example of training of label data. This is called zero shot. You have to classify without looking at any example. Okay. And this is when it started to get weird. Like how come these things work, right? So somehow, so just to give an intuition, somehow, because of the size of this data set, 40 gigabytes, most likely it has actually seen IMDb data. It just wasn't directed to that, saying like, oh, this is the sentiment analysis data set, this is named entity recognition. But it probably saw that information somewhere. And based on the context, it guessed the result correctly. And also, because of this size, it started to learn grammar, and it learned that if when you ask a question, you should answer, because after a question mark, there comes an answer, and all these things. So it started really to exhibit kind of like natural language capabilities, like in general. And then comes GPT-3, which is another really big leap, right? But now from 1.5 billion, we have 175 billion. So you have an idea of the size of this thing, right? And now you have 570 gigabytes of text. It's like another huge leap. And here, yeah, it's close to what we have right now. GPT-4 just came out recently, kind of. We don't know this information from GPT-4 because it's not public. So this tree actually, it's public. The OpenAI itself actually published this information. So here in GPT-3, we just saw that GPT-2 capabilities getting even better, right? So zero shot or few shot, like few shot capabilities is when you look at just a few examples. Let's say maybe 10 or 20 examples of sentiment data points. And so you give some information to the language model. Say, here is some examples of sentences classified with positive and negative, generalized from that. So this is few shot learning. Zero shot is where you don't give anything. And here, GPT-3 was actually the model that started doing question answering much better. And that actually enabled ChatGPT, because then you could ask things and interact with it. Okay, and then there was GPT 3.5, which is basically GPT-3, but with a twist, which was, so they saw this question answering capabilities in GPT-3, but they were really aware of kind of how these models would interact with people. Because they saw here that this model, for example, would have lots of biases. They would probably answer in a very rude way. You didn't have any control of how GPT-3 would answer people. So to build ChatGPT, or to build a commercial product, they had this idea of fine-tuning GPT-3 with reinforcement learning, which was very interesting as well. So we don't have time to talk about reinforcement learning, because it's a whole field of AI, right? But what was the idea? So they had GPT-3, and they wanted to have this kind of question and answering, right, system. But they were afraid that if people ask the question, the model would answer in a rude way, or maybe use curse words or anything like that, or just have a bad behavior. So to remove that, or to minimize this behavior, they fine-tune it with reinforcement learning. So it's like this. Fine-tune using, I'm going to draw this as a loop, because reinforcement learning can be thought as a loop. Basically what they did was they had GPT-3 here and a human on the other side. And the human would ask question and would observe the answer. If the human thought, oh, this is a good answer, he would give a bonus, or we would call it a reward. Okay, maybe like a +1 reward or -1 negative reward. So if it writes a bad answer, you say this is negative. When I say this is negative, is you change the models of the network based on these rewards. So you can think of this as this loop is going to generate a data set, right, of question answer 1, and this was +1. Question answer 2, this was +1, and then you have like a bunch of them. Maybe you have a -1 here. Question answer T, this was -1, right? And you have a bunch of these. So then you can retrain the weights of the GPT-3 based on this data set. Roughly speaking, it's something like this. Okay. So you produce a data set based on human interaction. And obviously these, the people who participated in this experiment, they were instructed to give positive feedback to positive behavior, right? And the idea here was to eliminate any bad behavior, right? Let's say if a racist comment or anything like that, right? Perhaps you would give like one -1,000,000 here or something, a really bad penalization or something. And this way they could kind of adjust GPT-3 to make sure it doesn't produce bad behavior. And that's why ChatGPT normally doesn't confront you, or even if you say like this is wrong, it will never say you were wrong. Or if you say something that is like factually wrong, let's say 1 + 3 is 5, it will like, nowadays probably it will like in a very nice way tell you that's not correct. But if you keep insisting, eventually it will actually agree with you, and then it starts hallucinating. because of that. Because it prefers not to confront you in any way. Right? Because for the company, that's much safer, right? Okay, so roughly that's what GPT 3.5 is doing, and that became ChatGPT right after, like, they did that. That became the first ChatGPT. And GPT-4 is what we have nowadays. The biggest improvement here is, again, on size. We don't know. So I looked it up. There is a lot of people estimating the size of ChatGPT. And there is a lot of sources that, this is just estimation. It's hard to, it's not confirmed. But several sources estimate that GPT-4 has 1.8 trillion parameters. Roughly like that. Okay? But it's not confirmed, so we don't know. Also, so we don't know the number of decoder blocks, and we don't know how much data they use to train. Okay, exactly. There is a GPT-4 report, which I'm going to link here. It's from OpenAI. It's a technical report, but it mostly discusses results of like natural language processing tasks, instead of actually talking about the method and the details of the model. Okay? But another improvement here was that this model is multimodal. So it not only understands text, but it understands images and audio as well. Okay, this is the overall evolution of GPT. Some other interesting comment is, even up to today, GPT-4 just is trained only to predict the next token, right? So it's a language model. It gets in a context and predicts a next word. And just from that, it knows how to answer questions and to do that, okay? Magically, if you want. So if you're still not surprised about these models, I don't know what will make you surprised, but for me, it's still really hard to believe that this simple language modeling thing does that. And there is other practical things. I know that OpenAI, when you ask a prompt, they actually they optimize your prompt. So whenever you write something on ChatGPT, they concatenate some other stuff to make the prompt. Like every prompt has some prepended text, something like, oh, you're going to act as a AI assistant or something. So answer the questions, blah, 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 blah. And then they concatenate your questions. Okay, so let's switch to BERT. BERT is very similar to GPT. But as I mentioned, BERT is an encoder-based model. It's a language model, but it's a masked language model. And the difference here is that, there should be a text here at the bottom. The difference here is that we're going to predict a word in the middle of the sentence given its left and right context. Remember, the encoder doesn't have a masked multi-head layer. So it can look at any any neighboring word, both in the left or in the right. It doesn't mask anything. So when you're training this masked language model, you grab a sentence, you remove a random word, and then you try to predict that word from the neighbor words, both from the left and from the right. So this mask token really just means blank space. I removed that word, and I want to predict glass there because that's the word I removed. And I do that for many sentences, like lots of sentences, and I sample these at random. So I just build a very large data set. But because of this property, BERT cannot generate text. Because it's not a regular language model where you're always producing the future, right? And then you can keep doing this loop of picking the output, concatenating back, and then keep generating text. So BERT doesn't do that. But it's very good at embeddings. And that's the purpose of BERT. BERT was designed for generating good contextual embeddings. And that's why most people will use BERT for extracting embeddings, even though you could do that with GPT. Okay? And it showed that it can do that. But back then, BERT was if you look at the paper, the results of BERT are better than GPT-4. So from that, they on, most people still use BERT for extracting embeddings. But the idea is the same. You train now a masked language model in unlabeled text using the encoder of the transformer. And here, literally nothing changed, right? So the encoder is exactly the same. But then you do the same thing. You freeze the model after you train your masked language model. You freeze the model to extract contextual embeddings. And your embeddings are going to come from the last block of the encoder. Okay? So basically, you would take the representations that are coming out of the last encoder. Remember, you have n encoders on top of each other, right? So you just get the last one. And then you do the same thing, right? You just freeze the model. You freeze the model, and then you add this classification head on top. Again, classification, just using a sentiment analysis example. And you can get same property of like, you don't change the models of don't change the weights of the frozen model. And then you're going to get a bump in accuracy for your classifier just by extracting these contextual representations. Okay, but the principle, again, is the same. We are just using the encoder and a different learning problem, which is now masked language model. And it's important that we don't use BERT for generation because of this masked language model formulation. Here is a similar evolution of BERT. We have many BERT models, but when it came out as two different versions. They called BERT base and BERT large, so I'm going to put them side to side here. So Google itself, I think it was Google Brain that released this model. They already released it in two different sizes, right out of the bat. So they're basically double the size in terms of encoder layers, right? So if the base one has 12 encoder layers, the large one has 24, and then 12 attention heads, and 16 attention heads. In terms of data size or pre-trained data set is the same. They trained on the same size of data set. And maybe here they will probably just fix the data set and increase the model to see how it would perform. And in this case, I'm assuming that 16 gigabytes was actually well suited for the large model. So the base model is just a smaller version of that. And well, these two models came out at the same time. They are just different sizes. So the contribution is roughly the same, right? But we can see that they were this very first bidirectional pre-training model. And we call it bidirectional because now we can look at the left and the right. But this is because of attention, right? Because the attention is not masked. Okay, so it can look at the whole context. And then there was Roberta, which was a just much bigger BERT, actually 10 times bigger, right, in terms of data set size, 160 gigabytes. But same size of encoder layers and attention heads. It just has like roughly the same amount of parameters as well, right? There was a huge line of BERT, and all of them were playing with these BERT names, right? And so distill BERT is actually a nice one because it's much more compact. So it has 66 million parameters, 6 encoder layers, 12 attention heads. It's trained on the same amount of data. And it's called distill BERT because it's a distilled version of BERT. So it has 40% fewer parameters and 60% faster inference. So it was used kind of for more real-time applications and actually thought as it was motivated by trying to make these models faster. So it's a much smaller model, but it retained almost the same performance, okay, 95% of BERT's performance on downstream tasks. And then there was Albert. Again, some other optimizations. Here, it's more like a technical optimization because you had less parameters with the same number of encoding layers and attention heads. So here they actually shared weights across heads, or across layers. Sorry. So they introduced this idea. And that allowed them to have 18 million parameters for the same 12 encoder layers and 12 attention heads of the base BERT. Okay, so this was a nice improvement of the model. So obviously, whenever these new models come out, people start to like kind of trying to optimize them in different ways. Okay. And then there is a Brazilian one which is called BERT in Bao, and I think it was trained at Unicamp as part of a, I think it was a master's dissertation. Yeah. Yeah, I think this is the dissertation. Yeah, here. It was, yeah, a master's. And basically, BERT in Bao is highly like similar to the original BERT, but trained on the Brazilian Portuguese corpus. Okay, so you have the BERT in Bao base and the BERT in Bao large. They have, I think, roughly the same amount of parameters of the original models, if I'm not wrong. And the dataset size was from, the difference is 5 gigabytes for the base model, 40 gigabytes for the large model. All Brazilian Portuguese text. And this was, as far as I know, but I mean, this is not probably hard to prove, that this was the first large-scale pre-trained model for Brazilian Portuguese. At least one that people started using and like really became popular. And it's similar, comparable to the original BERT in Portuguese. Okay. And just one practical discussion here to finish. We can extract contextual embeddings from BERT in different ways. So there's many different approaches. And why are there multiple approaches? So when you look at the output of the, this is an encoder, but the decoder is the same. When you look at the encoder output, you're going to get a list of vectors. It's a matrix, right? Where each column is an embedding of the word T. So C1 is the embedding of the word 1. So I wanted a glass of orange juice. C1 is a contextual embedding of the word I. And C2 is a contextual embedding of the word want, and so on and so forth, right? So this is a vector. This is a vector. So if you just want the embedding of the word, you can just go there and extract the vector at that position, right? If I want the embedding of the word orange, I would just get the column 1, 2, 3, 4, 5, 6, the sixth column. That's the embedding of the word I want. But there's one cool thing that we can do with transformers that we were not doing with Word2Vec, which is modeling whole documents, because BERT processes sequences, right? So we can now have an embedding for a document, for a paragraph, for a whole like document if you want. And one way, the simplest way of doing that is just averaging all these vectors. Okay. That would give you one vector that represents the entire sequence. So if you want to get one embedding for this sequence, you just get all these vectors, sum them, and divide them by the number of vectors, and that's your sentence. Okay? And this is very powerful, because I can have a vector for a document, right? And for example, Google is using these ideas for doing page ranking. Right? I can get a web page, pass it through a BERT model, and get a vector, and I can do that for any other web page on my database of web pages of the whole internet. And now I can do ranking based on similarity, right? I can have like all my, so Google does that, right? So it has all the documents, all the web pages on the internet, right? And I can feed this to BERT, and this to BERT as well, and this to BERT as well. And I get a vector, which is the average of all of the vectors of all the words in the web page. And now if I have a query, which is just another sentence, right? Maybe, Universidade Federal de Viçosa, which is 4 words. This is a sentence. I pass the sentence into BERT as well. I get a vector. And now I just compute cosine similarity. And I rank these pages based on similarity. Okay. And because BERT knows position, it tends to be much better than the queries Google does classically, in the classical retrieval way. Because, for example, I don't know if you know, if you have noticed it, if you try to buy a bus station or a bus ticket from Viçosa to Belo Horizonte, Google originally didn't know that you wanted a ticket from Viçosa to Belo Horizonte and not the other way around. So it didn't consider the order of the query. But now with BERT, it can actually know that you want a bus from here to there, not from there to here. And the queries can get much better now because of these approaches. So this is just one idea you could do with BERT. And what is cool is that, remember, you still have those embedding properties. So if the documents are similar in space, are about the similar things, they will be similar they'll be closer in that space. Okay, so this is very powerful for many research applications that is related to maybe like legal documents or whatever type of application you're trying to do, right? Anyways, you could discuss this a lot. I have a cell here with these approaches for you, okay? So this is a code that can extract embeddings using these methods. And then you can use this to play with this code. This is using BERT to extract embeddings. So here you have just getting the less hidden state. And in this approach, you just get one vector per word. And this is useful for doing, for example, if you want to do named entity recognition, you want a vector per word, right? So you want a vector for each of these words. Then you probably want just to take this approach here, the hidden state. But if you're doing sentiment analysis, you might just want to get one vector per sentence. Then you maybe just want to average them. Okay, so there's different ways to extract embeddings. I just want to give them here to you because this is very useful. Okay, and that's all for today. Next week, we don't have the exam. We're going to talk about transfer lane. Okay, thank you.